Hi, everybody. Thank you for being here. My name is Mina. I'm working for IMEC, and I'm responsible for the field application engineering team at IMEC, working most of the time with the spectral imaging technology. I'm honored to be here to present one of our ongoing projects together with ILIA in Belgium, which is about drone-based corrosion monitoring of metallic towers using a spectral imaging technology. Sorry, the pointer? Is it this one? Yeah. OK, thank you. So IMEC was founded in 1984. It's actually a pioneer in semiconductor technology. We have more than 5,500 people from different nationalities working for IMEC. And our core expertise, we are actually technology providers to enable you for your industry-related application to find out the best solution for your application. So most of our revenue is actually more than 70% of our revenue is coming from collaborations with industry. So you can see that we have more than 600 industrial partners that we work with. And that's actually our main goal, our roadmap to work more and more with industry. IMEC is based in Leuven, Belgium. Here is the aerial picture of our site. On the left side, you see the 200-millimeter clean room. On the right side, we have the 300-millimeter clean room, which is the world's most advanced pilot line for prototyping. On the left-hand side, on top, we have our imager labs, where Spectral Imaging Labs is located. And we are also working on integrated imaging and other imaging-related technology and development. So what is unique about our technology at IMEC is that we are actually reducing so many of the components that was in the traditional spectral imagers, such as the grating and also the prism and other related components to that. And then we can actually deposit the color filters directly on the sensor. So by that, we can actually make much smaller cameras that can be used even on a handheld device or on many other different tools that you can easily use them in the lab or in the field. So on-chip spectral imaging filters is scalable, and it can actually be miniaturized, and it's very robust. And by just doing the snapshot, for example, imaging, we can actually get video or real-time imaging that can help for many industrial or machine vision applications. We have spectral cameras in different range, all the way from visible range to near-infrared and short-wave infrared, which is from 1,000 nanometer to 1,700 nanometer. So as I said earlier, we actually design and manufacture spectral filters, and we deposit them directly on the chip. For example, here you can see a color filter, a mosaic pattern that has been deposited on the sensor. And then we have a 4x4 Bayer pattern, which provides you with 16 spectral bands in the visible range. And then it can actually be used for snapshot cameras that, as I said earlier, we can actually use it for real-time imaging and sensing. So here is a video that you get different spectrum from different leaves and materials. And then you see the pattern of the spectra is very different. And based on that, we can actually have a classification map that we can see on the very bottom right corner. And if you activate the live streaming, you can see that the classification map is still following the specific material that is moving in the scene. So this is unique about our application, that we can actually do spectral analysis on real time. We have also devices or the cameras that can be used for handheld devices, or it can be used on a moving platform like a tractor in a farm or between the trees. So we can actually take care of both the movement of the platform and also the movement of the trees or the leaves, which is really robust. Our sensors also has been used on a unit that can go on a drone platform, and it's used for some agriculture applications. And also, I'm going to show you that in this application related to corrosion monitoring, we also used this specific sensor on our drone payload. But we also have provided sensors for satellites for remote sensing of the Earth and the land covers of the Earth. So in this specific project, as I said, we actually tried to monitor corrosion on the high voltage metallic towers. Why did we decide to do that? Because inspecting corrosion on high voltage tower is a very risky and time-consuming process. It usually requires people to climb the towers, which is very risky, and it's also, you have to turn off the whole power, and it's not really beneficial, and it's time-consuming. People have tried to use RGB imaging on the drone to be able to differentiate corrosion from coating, but with RGB imaging, we are limited to only first visible range and also limited bands, so the false positive was actually very high. And that's why we decided to use a spectral imaging for this matter, because you get more information from different ranges, visible, near-infrared range, and you have also more information. So you have more than 3 bands, and that can enable you to specify where the corrosion or the other surface anomalies are. We started this project by some feasibility study in the lab. So we received some samples from a real demolished tower. These samples were from different types of coating and different types of corrosion that was occurring on them. So we made a lab setup, and we scanned the samples under controlled light condition, one by one, with 2 different IMEC snap scan cameras. So with both VisionSTR, which has 150 bands in the visible to near infrared range, and also with a SWIR, a snap scan camera, which has more than 100 bands in the SWIR range. And we could see that actually with the results of our laboratory test that we can actually detect corrosion, and not only detect corrosion from the paint, but also sometimes we can see the difference between different types of corrosion. If it's a superficial corrosion or if it's a severe corrosion, that can also be distinguished by spectral data. Also, we did some other tests in the lab that we put some other surface anomalies that look like corrosion in the visible range to just see if we can get use of the spectral information to mask out the outliers. For example, in this case, we put a dry leaf, and also we put some soil on the samples, and you can see that the spectral behavior, in this case, in the near-infrared, it's completely different from the corrosion. So that means that we can actually differentiate corrosion and the other surface anomalies on the towers. Then we went one step forward. We actually put the same samples outdoor because we wanted to see how the spectral behavior changed under ambient light and all this atmospheric condition. In this case, we used the snapshot cameras, both in near and in the SWIR. And then we analyzed the data. We also used our first drone prototype to look at the way that we can actually scan a real tower. This prototype has 2 snapshot cameras from IMEC in vis and in near spectral range with more than 30 bands. So we defined also a workflow that we start from acquiring hyperspectral data from this drone unit that we have in the vis and in near spectral range. We correct the data. For example, if it's demosaicing is required or the spectral correction is required, we do all the pre-processing. Then for the segmentation of the tower, because it's important that we can segment the 3D reconstruction of the tower, we can segment the tower from the background. Sometimes the towers are located in a farm with like vegetations as background, so we wanted to do the segmentation to only see the towers. And also it's important to go to the element base. So corrosion is happening on different parts of the tower, but for the company that we are working for, it was important to know on which element this corrosions are occurring. So we can also segment the tower based on the different elements. And at the end, we go to the classification. For the classification, we use the paint spectrum as a reference spectrum for calibration, because it's very difficult to put a white tile outside. It's not really possible, because we're also with the drone is moving. We are moving around the tower. So we decided to use the paint spectrum as the reference spectrum, and we calibrated based on that. Then afterwards, we did the outlier detection with our classifier. And at the end, we used the fully constrained least square unmixing for detecting corrosion from the paint. Also, for the accurate 3D reconstruction model of the tower, we added a LiDAR sensor to our drone payload. So this was a hardware and also software integration into our existing drone unit. And you can see that with using the LiDAR data, we can actually get a more robust 3D reconstruction from the tower based on the position of the cameras and also based on the LiDAR information. This was actually also improved by adding a lens with higher focal length. So the lenses that we were using on this drone payload was only 24 millimeter focal length, but we also use 50 millimeter focal length lenses, and then we could actually get also a very good 3D reconstruction from high resolution, higher spatial resolution, hyperspectral data. So if it's a really accurate model, we can go for the LiDAR, but if we want, let's say, average 3D reconstruction to high accuracy, then we can use the hyperspectral data by just using a better lens. So at the end, the results of this project was showing that we can actually differentiate corrosion from paint on the high voltage metallic towers. We can also get a 3D reconstruction model from the towers by using either LiDAR data or by mounting high resolution lenses on our hyperspectral data. We also add the HDR feature to our software to be able to collect data from different integration times, because it's also important for segmentation of the tower to sometimes if you have shadow or if you don't have enough light, then it's better to have multiple integration time acquisition. So that was also helping us for this 3D reconstruction segmentation of the different parts of the tower, and this was an added value for us. We also realized that the near data is a useful range for detecting the corrosion, and it's also providing the highest signal-to-noise ratio, because sometimes when you're going outdoor, the SWIR data cannot really provide the high signal-to-noise ratio. The outliers were also differentiated from the corrosion, so that was also one of the added value compared to the RGB imaging. And so far, our classification models have been validated on the lab data. We had samples both inside the lab and outdoor that we could actually get the ground truth information and validate our classification. But for the outdoor data that we have collected, we are still waiting for the ground truth. And so far, we have been scanning several towers. They didn't have really that much corrosion, but yesterday, my colleagues were actually in a site with a tower that had a lot of corrosion, and then we're hoping to be able to validate our classification software on this specific tower. So IMEC, as your technology partner, we're actually providing you with both off-the-shelf camera, but we can also go for custom design cameras or filters based on your application. So you can see that we can actually, we have a roadmap of starting from feasibility study for your specific application and see which specific wavelengths or which specific spectral ranges are more useful for your application, all the way to the proof of concept and prototyping. And we can even do some low-volume manufacturing, like up to 500 wafers per year at IMEC. And we can also, for high-volume manufacturing or production, we can transfer the knowledge and the procedure to the production labs that are bigger than IMEC, and they can provide you with high-volume production. So thank you very much for listening to this presentation. I would be happy to visit you also on our booth. And if you have any question, I'm here to answer your questions. Thank you.
Thank you, Mina. Another very interesting application.
Applications, indeed.
Of hyperspectral imaging. Questions from the audience? I don't see any.
OK.
So maybe you mentioned it, but I don't remember it. I have a question.
Sure.
I was informed by a drone manufacturer that it's very difficult to find a camera that's not too heavy.
Indeed. And that's,
so may I ask which camera you use?
Yeah, indeed. That's actually the advantage of IMEC cameras that are actually very small in the form factor, and they're also very light. That's why we call it miniaturized spectral camera or spectral filters. So they can actually use them easily on drones because it's actually very low light, maybe in the matter of few hundred grams. And that's not going to be a problem for any drone application-wise. Yeah.
OK. So maybe I was not attentive enough. So you produce cameras, and you then use them for applications.
OK, so maybe I should explain better that our core technology or our core expertise at IMEC is providing sensors. So we're actually depositing color filters on the sensors. The sensors can be just CMOS sensors or any other sensors that we get from the partners. And we have some off-the-shelf cameras because, of course, we want to know where we can actually use these cameras, but we are not really camera manufacturers. So we can actually even give the sensors to people who work with the laparoscope, for example, in the surgery room, and they can integrate either the small cameras that we have, or they can just put the chip inside their sensing tool, and they can integrate it into their own sensing tool. So that's actually the benefit of using IMEC sensors or IMEC spectral filters, because they're actually it's easy to adapt and integrate it into a new, let's say, sensing tool.
OK, so thank you for your explanation. Now I
You're
got
welcome.
it.
Thank you.